The cellular telephone is a major part of the ongoing telecommunications revolution. The ubiquity of this device has changed our lives in profound ways. And for this reason alone, we should know something about the underlying technology. I'm sorry. But cellular technology is also worth knowing about because it's often more problematic than the other technologies in our lives. Why do I get good service in some areas and bad service in others? Why do I sometimes lose my connection for no apparent reason? Why does my battery consumption seem to vary so wildly? Why did they build that ugly antenna tower in my backyard? Well, as you know, I'm a strong advocate for being an informed user of technology. Today, I hope you'll come to recognize that being an informed user of cellular technology can be particularly beneficial. At the most fundamental level, cellular communication involves analog or digital encoding of a radio carrier signal. Thus, we can't understand the technology without first understanding radio. Anytime electrons move at varying speed, they generate electromagnetic radiation that propagates through space at the speed of light. We've seen this phenomenon before. The reason twisted copper wires are twisted is to reduce the adverse effects of electromagnetic radiation emanating from the wires as current flows through them. Coaxial cable uses a metal shield to contain the electromagnetic field within the cable and to protect against electromagnetic interference from outside. Because electromagnetic radiation oscillates as it propagates through space, it's characterized as a wave phenomenon. And like any wave phenomenon, it can be classified according to its frequency. The electromagnetic spectrum, with its associated frequencies, is illustrated here. At the bottom end is low-frequency, long-wave radio. The progressively higher frequencies are conventional radio, including the frequency bands used for AM and FM radio, then microwave, infrared, visible light, ultraviolet light, X-rays, and gamma rays. By the way, these low-frequency radio waves are called long waves because the physical length of a wave is inversely proportional to its frequency. The 30 Hz radio waves used by the US Navy to communicate with submarines are over 6,200 miles long. FM radio waves, transmitted at 100 megahertz on your FM dial, are about 10 feet long. Microwaves at 10 gigahertz are about 1/100th of an inch long, so small that they can be scattered by raindrops, which explains why microwave communication signals can be degraded by rain and fog. In general, electromagnetic waves with low frequency can travel much farther than those on the opposite end of the spectrum, but they have significantly lower capacity for carrying information. Electromagnetic waves with high frequency have far greater capacity by virtue of their greater bandwidth, but they also attenuate more quickly. And as we've seen with microwaves, their waveforms are so small that they're highly susceptible to atmospheric interference. For these reasons, most wireless communications use the middle of the electromagnetic spectrum. Mobile phones generally operate primarily in the frequency band just above FM radio, from about 700 to 2500 megahertz. So, how does radio communication work? Well, in general terms, a transmitter generates an alternating current that's been modulated or electronically mixed with a signal representing the information that's being transmitted. This alternating current is passed through an electrical conductor called an antenna. And because the current is oscillating, it generates electromagnetic waves at the same frequency as the current. These waves radiate off the antenna into space at the speed of light. As long as the frequency of the alternating current is in the radio frequency range, the resulting electromagnetic waves will be radio waves. At the other end of the transmission, the process happens in reverse. The electromagnetic waves impinge upon the receiving antenna, introducing a corresponding electrical current. This signal can then be demodulated to retrieve the transmitted information. Now, antennas can be designed to transmit and receive in all directions, like this one on my walkie-talkie. Or they can be designed to focus electromagnetic waves in a particular direction, as we saw with the directional antennas used on microwave relay stations last lecture, and as we'll see with parabolic satellite dishes in the next lecture. And so we come to the cell phone, which is really just a radio transmitter receiver. In this sense, the cell phone isn't really new technology. It's not fundamentally different from those walkie-talkies we see in the World War II movies, with two exceptions. First, a walkie-talkie typically operates on only one radio frequency, so you can either transmit or receive at any given time, but not both. Most cell phones operate on two frequencies to facilitate simultaneous transmission and reception, called full duplex communication. Now, I say most because a recent technological innovation actually allows simultaneous two-way communication on a single frequency, as we'll see later in this lecture. Second, those original walkie-talkies were all analog devices. And while the first generation of cell phones was analog as well, all modern mobile devices encode and transmit information digitally. Although the cell phone itself is conceptually similar to a simple walkie-talkie, what makes cellular networks so complex is the need to handle millions of conversations simultaneously. The electromagnetic spectrum is a finite resource. If we start handing out 2 frequencies per mobile phone, we'll run out of frequencies long before we run out of mobile phone users. Cellular networks handle this challenge through a concept called space division multiplexing. A geographic region is subdivided into a regular grid of smaller areas called cells. And yes, that's why it's called a cellular system. Each cell has its own antenna and base station. Taking a hint from nature, these cells are normally hexagonal, like the cells of a honeycomb, to provide efficient coverage with minimal overlap. Within each cell is a base station, which incorporates the radio transmitters, receivers, and antennas that communicate with all mobile devices located within the cell. The power of the radio transmitter is deliberately limited so that frequencies can be reused in other cells without causing interference between transmissions. But which other cells? The answer to that question depends on a factor called the cellular reuse pattern. The first generation of commercial cellular technology was launched in Japan in 1979 and called 1G for first generation. In this system, each cell was about 8 miles wide, and the cellular reuse pattern was 7, meaning that each cell of this 7-cell module used a completely different set of frequencies. Now, when we replicate this reuse pattern across the countryside, we see that it always provides a buffer of 2 cells between any pair of cells using the same frequencies. For example, any 2 yellow cells have 2 non-yellow cells between them in any direction. Now, the electromagnetic spectrum is a highly constrained resource, and so it's tightly controlled by government regulatory agencies like the U.S. Federal Communications Commission. In 1G networks, the FCC typically allocated enough radio spectrum to provide each service provider with 832 voice channels. That is, 832 discrete frequencies that could handle simultaneous voice communications without interference. 832 channels allow for half as many two-way conversations, or 416. With a cellular reuse pattern of 7, these channels had to be allocated equally among the 7 cells in each module. As a result, each of those 8-mile diameter cells in the 1G system could serve 416 divided by 7 equals 60 simultaneous conversations. Accommodating 60 phones within an 8-mile diameter was a revolutionary capability back in the 1980s. Today, it probably wouldn't even be good enough to qualify as inadequate. And so, the history of cellular technology development since then has revolved around the need to handle an ever-increasing number of users, demanding ever more bandwidth for both voice and data communications, and ever more reliable and responsive service. One response to these challenges has been simply to to use more efficient cellular reuse patterns. For example, this one is based on a 4-cell module, which still provides a buffer of 1 cell between each pair of cells operating on the same frequencies. This simple change allows for the use of 75% more frequencies per cell, with a corresponding increase in the number of users. However, the smaller buffer between the common frequencies also requires the use of antennas with more precise control of their coverage areas to minimize the likelihood of interference. One common technique for achieving better coverage has been to place the antennas not at the center of each cell, but rather at 3 of the corners, like this. With this configuration, directional antennas are now used to limit each tower's coverage more effectively to the assigned cell. Note also that in this configuration, each cell is served by 3 different towers, providing more uniform coverage, and each tower covers 3 different cells. And that's why, at the top of most cell towers, you'll find triangular arrays of directional antennas like this one. Each side of the triangle is covering a different cell. And viewed from a different angle, we can see that each antenna is angled slightly downward here to ensure that transmissions don't overshoot the cell and cause interference. Another response to the need for greater capacity has been to use smaller cells in areas where larger numbers of users are congregated. The capability to subdivide big cells into little ones like this was an important new feature of the 2nd-generation cellular network standard, or 2G, which was first deployed in 1991 in Finland. Since then, we've seen the establishment of microcells, each about a mile wide, picocells, typically 500 feet or less, and even femtocells on the order of 30 feet. Now, picocells and femtocells are often used to extend cell coverage indoors, the former for office buildings, shopping malls, train stations, and similar large public facilities, the latter for small businesses and even individual homes. Beyond the improved coverage, smaller cells also have the advantage of requiring less power at the base station and in your phone. And yes, today, most cell phones do have variable power output, and the cellular base station actually controls your phone's power level to maintain an adequate signal while minimizing drain on your battery. But this relentless subdivision of cells has some significant downsides too. Obviously, one is the added cost of more antennas, more base stations, and more network interconnections. Evidently, this cost is being met by the ever greater number of subscribers that these smaller cells are serving. So perhaps it's not a significant issue. But a much more significant drawback of smaller cells is a larger number of handoffs, which occur every time a user moves from one cell to another. We'll talk about how handoffs work shortly. For now, it's only important to recognize that the handoff is a complex process requiring considerable computation and information exchange between your phone and the cellular network. Consequently, demanding too many handoffs in too short a period of time can cause problems. Often this challenge is addressed by using macro cells, sometimes as large as 20 miles across, in rural areas and along highways where users are most likely to be crossing from cell to cell at higher speeds, and by using smaller cells in areas where people are likely to remain in one cell for relatively longer periods of time, like shopping malls and office buildings. But what happens when a highway runs right through the middle of a densely populated metropolitan area like this? In such situations, many modern cellular networks use umbrella cells, which provide redundant wide area coverage overlaid onto a grid of smaller cells. In this arrangement, when a microcell detects a mobile device moving at very high speed, it hands off the call to the umbrella cell, thus significantly reducing the subsequent number of handoffs. Allowing the use of variable cell sizes contributes significantly to enhanced capacity in 2nd generation or 2G cellular networks. But the most important contributor by far was the change from analog encoding in 1G to digital encoding in 2G. This change allowed for the encryption of voice transmissions, addressing a particularly serious security concern with wireless communications, and it opened the door to the transmission of data as well as voice. Text messaging, officially the Short Message Service or SMS, was an integral part of the 2G standard, and it paved the way for the smartphones of today. But most importantly, the switch from analog to digital allowed for significantly more efficient use of the limited electromagnetic spectrum assigned to cellular communications because it incorporated multiplexing, or to be more precise, it incorporated more sophisticated forms of multiple access. So what's the difference between multiplexing and multiple access? In 1G networks, the simple system of allocating two frequencies to each user is called frequency division multiple access. The concept is quite similar to frequency division multiplexing, which we discussed last lecture in the context of wired networks. But there's a subtle difference. In multiplexing, multiple conversations are combined into a single signal for transmission through a wire. In a wireless network, the individual conversations are transmitted independently between various mobile devices and the cellular base station. This is multiple access. The major technological advance in 2G networks was a new system called time division multiple access, which actually combines the concepts of frequency division and time division multiplexing. In time division multiple access, the entire available frequency spectrum is first subdivided into channels, as was done with frequency division multiple access. And then, within each channel, as many as 8 different phones are each assigned a specific time slot for transmission. The phones then transmit in short bursts within their respective time slots in rapid succession. Each cycle of 8 transmissions is so short that users perceive their conversations as continuous, even though they're actually a series of discrete samples. Now, by itself, time division multiple access provides an 8-fold increase in capacity over the simpler frequency division system used in 1G networks. But with increased capacity comes a significant new technological challenge: synchronizing transmissions by mobile devices located at different distances from the cellular antenna. Even though radio waves propagate through space at the speed of light, the time slots allocated to each burst of data are so small that the time it takes a transmission to travel across a cell can actually cause a given burst to miss its assigned time slot. To compensate for this travel time, the base station calculates something called a timing advance for each phone and sends that information to the device. The phone then sends its bursts of information just a little bit earlier by the amount of the timing advance, so they arrive at the antenna at precisely the correct moment. This system works well when the phone is standing still. But when the phone is in motion, there's typically some lag in matching the timing advance to the phone's actual position. Thus, to prevent interference, a small chunk of time needs to be inserted between the assigned time slots in the transmission sequence just to provide margin for error. And this added time robs some of the efficiency gained through time division multiple access. Now, this limitation has been very effectively addressed in third generation or 3G wireless networks, which were first deployed in 2001. Most 3G networks accommodate multiple users through a fundamentally different approach called code division multiple access, also called spread spectrum. In this system, there's no subdivision of the available spectrum into smaller frequency bands. Rather, all users within a given cell are communicating across the full spectrum at the same time. In this system, your mobile device modulates its original signal with a unique, randomly generated code that's provided by the base station. During this process, the bandwidth of the transmission is effectively spread across the full available spectrum, but it's done with a unique pattern that can be recognized and decoded by the receiver. Now, code division multiple access is very difficult to visualize, so let's try a simple analogy. Have you ever been in a foreign country, in a public place where lots of people are talking simultaneously in a language you don't understand? All you hear is a cacophony of unintelligible sounds. And then suddenly, you hear a single voice speaking in your own language. And as soon as you discern the unique and familiar pattern of speech in your own language, you're able to lock in on that single voice and filter out the undecipherable cacophony of the other voices in the room. This is the essence of code division multiple access. And in a cell network, this system uses electronic spectrum 10 to 20 times more efficiently than the simple frequency division scheme used in 1G networks. It also produces further increases in capacity by reducing the cellular reuse pattern to 1. In other words, the code division multiple access system allows for adjacent cells to operate on exactly the same frequencies without interference, as long as these adjacent cells use different codes. This feature represents another 7-fold increase in the number of users per cell in comparison with the reuse pattern of the 1G network. The efficiencies gained from this system arrived just in time to accommodate the explosion in demand for mobile connectivity that accompanied the introduction of the iPhone in 2007. But demand has only increased since then, as consumers have increasingly come to rely on their mobile devices for such functions as internet access, streaming video, gaming, voice over IP, mobile television, video conferencing, and cloud computing. To address these demands, enhanced 3G and recently introduced 4G systems have incorporated such features as advanced antennas that can transmit multiple parallel data streams simultaneously, data compression to pack more information more efficiently into a communications channel, duplexing techniques, which allow a single channel to share both the outgoing and incoming halves of a conversation, and new schemes for multiple access that, I must admit, are essentially indistinguishable from magic. All of these changes require an extraordinary level of coordination between the research and development community, government regulators, standards organizations, both domestic and international, wireless carriers, and hardware and software developers. And this challenge can only ever be met temporarily because demand is ever increasing and new technological paradigms are constantly emerging. The 5G standard is due out in 2020. Watch for it. It's hard to imagine a more dynamic and unpredictable context for technological development. Well, up to this point, we've discussed the radio communication link between your mobile device and the nearest cellular base station. But this is really only the tip of the iceberg. The base stations are just intermediate nodes in a far more extensive network of networks, illustrated here. Tens or even hundreds of base stations are connected to devices called base station controllers, which in turn are tied together by regional facilities called mobile switching centers. And by the way, the links between these base stations and controllers are usually landlines, but occasionally microwave links, as is the case with this particular station. The mobile switching center operates like a local exchange in the public switch telephone network, and indeed, it also provides the interface between the cellular network and the PSTN. The mobile switching center sets up and releases end-to-end calls, both mobile to mobile and mobile to PSTN. As the diagram indicates, base station controllers are also connected to the general packet radio service, a packet switched network that's overlaid on top of the circuit switched phone network and handles all internet data packets passing between your mobile device and the internet. Another critically important function that's performed jointly by the base station controllers and the mobile switching centers is the handoff of calls from cell to cell. Here's how this process works. Anytime you turn on your phone, it tunes into a specially designated frequency called the control channel, and it listens for something called a system identification number, which is broadcast by each base station to identify the associated cellular service provider. If your phone can't find a system identification number, it displays that annoying no service message. Your device knows the system identification number of its own service provider, so if it detects this number being broadcast, it knows it's operating within the coverage area of its own provider. If not, it's roaming within a different provider's area. On the same control channel, the phone then identifies itself to the service provider, and the mobile switching center stores the phone's location in a database. Through this mechanism, the system knows where your phone is located whenever it's switched on, so the associated mobile switching center can find you when someone dials your number. Now, when a call does come in, Your switching center looks up your location in the database and then communicates with your phone over the control channel, sending you a ring signal and all the necessary coordinating information to complete the connection. For example, in a time division multiple access system, it provides the two frequencies and the time slots for transmission. In code division multiple access, it provides the code. When you answer the phone, you've got an end-to-end connection to the person who's calling you. Now, let's say that you're driving while the call is in progress. The base stations covering your cell are constantly monitoring the quality of your signal as measured by the signal strength, error rate, voice quality, and other metrics. When these measurements indicate that you're approaching the edge of your current cell, the base station controller, or in some cases the mobile switching center, coordinates with the adjoining cell, called the target cell, to effect a handoff. At the appropriate moment, your phone receives a signal on the control channel telling it to change frequencies, or in a code division multiple access system, to start using a new code. Once the switch is made, control of your call transfers to the target cell. In some systems, this changeover happens instantaneously. In others, there's a short period in which you remain connected to both cells and your phone can choose the stronger signal. In either case, the handoff is usually so precisely controlled that it can occur in the middle of a word and you won't notice it. Calls do occasionally get dropped during handoffs. When this happens, the most common reason is that the target cell doesn't have an open channel to give you. Now, in many ways, cellular communication is indicative of our love-hate relationship with technology. Even as we demand better coverage, better speed, and more wireless services, we staunchly oppose the construction of that ugly antenna tower in our neighborhood or on that picturesque hilltop out in the countryside. But not in my backyard really doesn't work very well with cellular networks. Coverage requires proximity to an antenna. And once the geometric grid is established, the corner of a cell falls where it falls. The cellular provider just doesn't have that much flexibility to move it around. Granted, competing service providers often exacerbate this problem by establishing their own independent systems of antennas. Thus, it's not unusual to see two cell towers standing on top of the same hilltop, like this. Fortunately, the level of conflict over this issue does seem to have abated somewhat within the past few years. These days, there seems to be less opposition to the construction of towers, perhaps because they've become so ubiquitous that we hardly even notice them anymore. And the service providers have done their part in exercising more creativity in the design and placement of their antennas. Consider just a few examples. It's now quite common to see cellular antennas grafted onto water towers and power transmission towers. Now, these installations are certainly no less ugly than standalone towers, but they are effective in concentrating ugliness in one location so that some other location might be spared. Particularly with the advent of microcells and picocells, it's now common to see cell antennas placed on the roofs of commercial buildings rather than on standalone towers. And in rural areas, well, you've got to love the antenna disguised as a stately pine tree, and in tropical climates, as a palm tree. These cellular cacti aren't terribly convincing, but they're a noble effort nonetheless. And here's my personal favorite. On the steeple of this beautiful old church in Poland, this antenna is perfectly disguised with trompe-l'oeil brickwork. Now that's an accommodation between aesthetics and technological necessity to which we can all aspire. Next lecture, we'll take wireless communications to a higher level with satellite communications. In this lecture, we'll explore an everyday technology that very few of us have ever actually seen or will ever see, the satellite. Now, in one sense, no other technology we've discussed in this course is quite as remote from our day-to-day experience. Satellites are literally out of this world, orbiting hundreds or even thousands of miles above the Earth's surface. Yet, I don't think I'll have any problem convincing you that satellite technology belongs in this course on everyday engineering. Satellites directly influence our daily lives when we check tomorrow's weather forecast, watch satellite TV, listen to satellite radio, watch a live TV news feed transmitted from a remote location halfway across the globe, or use a GPS device for navigation. There are 7 major types of satellites. Communication satellites facilitate global telecommunications in a wide variety of forms: television, radio, internet, telephone, and specialized business transactions. Navigation satellites are used to determine locations on the Earth's surface or in the air by transmitting radio signals to mobile receivers. Reconnaissance satellites are used for military and intelligence purposes, including high-resolution photography, communications interception, covert communications, monitoring nuclear test ban compliance, and detection of missile launches. Earth observation satellites perform non-military observation functions, such as environmental monitoring, meteorology, and map-making. This category includes National Weather Service satellites used for weather monitoring and forecasting. Astronomical satellites are used for observing distant planets, galaxies, and other heavenly bodies. The Hubble Space Telescope is a good example from this category. Scientific satellites are used to perform scientific experiments in such fields as biology, chemistry, metallurgy, botany, and medicine. Finally, a space station is a satellite that's inhabited by humans. The International Space Station is the most recent example of this technology. There are currently over 1,000 operational satellites in Earth orbit, owned all or in part by over 100 different countries. These represent a diverse mix of all 7 types. Some are military, some governmental, some commercial. In this lecture, we'll look at 2 types of satellites that have the greatest direct impact on our everyday lives: communications and navigation. But first, we'll need to review a few basic concepts in the science of orbital mechanics. Yes, this is rocket science. Modern orbital mechanics has its roots in Kepler's laws of planetary motion, first published by Johannes Kepler in 1609, and in the more general laws of universal gravitation and celestial motion, published by Sir Isaac Newton in his monumental work, Mathematical Principles of Natural Philosophy, in 1687. For the purpose of today's lecture, there are 5 key concepts in orbital mechanics that we need to understand. 1. A satellite's orbit is elliptical, with the planet located at one focus of the ellipse. 2. On an elliptical orbit, the closest point to the planet is called the perigee, and the farthest point is the apogee. 3. A line drawn from the planet to the satellite sweeps out an equal area in an equal period of time at any location in the orbit. Thus, the satellite moves faster when it's closer to the planet and slower when it's farther away. 4. Once a satellite is in orbit, the orbit's characteristic shape and orbital period won't change unless the satellite is subjected to an applied force, such as thrust from a rocket engine or drag caused by interaction with the atmosphere. And 5. As the 2 foci of an elliptical orbit get closer together, the shape of the orbit becomes progressively closer to a circle. Mathematically speaking, the ellipse becomes progressively less eccentric. Thus, a circular orbit is really just a special case of an elliptical orbit, one for which the 2 foci correspond. For a circular orbit, the altitude of the satellite, that is, the distance from the Earth's surface, never changes. Thus, its speed must be constant. And according to Kepler's laws, both the speed and orbital period for a body orbiting the Earth can be calculated using these 2 equations, where r is the radius of the orbit, and the Greek letter mu is a number called the standard gravitational parameter. which, if you're interested, is actually equal to Isaac Newton's universal gravitational constant times the mass of the planet. What's really important here is that the speed and period of a circular orbit depend only on its radius, not on the mass of the satellite. To illustrate the use of these equations, let's consider a satellite in a circular orbit with an altitude of 100 miles. Now, the radius of this orbit is its altitude, 100 miles, plus the radius of the Earth, 3,960 miles. Substituting, we find that the satellite orbits the Earth in under 1.5 hours, and it moves at over 17,000 miles per hour. Earth orbits are generally classified in 4 categories. A low Earth orbit, or LEO, is a circular orbit with an altitude between 100 and 1,240 miles above the Earth's surface. Note that the example we just worked is a low Earth orbit. The medium Earth orbit is a circular orbit with an altitude between 1,240 and 22,236 miles. At the precise altitude of 22,236 miles is the geostationary orbit, or GEO. We'll return to this very special orbit in just a moment. And finally, the elliptical orbit is used to transfer a satellite from one circular orbit to another, as we'll see shortly, and for other special purposes. Now let's see why the geostationary orbit is so special. Using our orbital mechanics equation, the orbital period of a geostationary orbit works out to be 23.93 hours, which is exactly equal to 1 sidereal day. A sidereal day is the time it takes for the Earth to complete one full rotation with respect to a non-rotating frame of reference. Watch. On this diagram, the Sun is directly overhead at this particular location on the Earth's surface at time 1. Now, at time 2, the Earth has rotated through exactly 360 degrees. But because it's also revolved 1/365th of the way around the Sun during the same period, the Earth must now rotate just a bit more before the Sun is directly overhead once again. The period of time from 1 to 2 is a sidereal day of 23.93 hours, and from 1 to 3 is our standard solar day of 24 hours. Because a geosatellite's orbital period exactly matches the Earth's rotational period, the satellite remains perfectly stationary at one point in the sky from the perspective of an observer on the Earth's surface. That's why we can aim our satellite dishes at one point in the sky and never have to adjust them. That's why most communication satellites use geostationary orbits. By the way, the concept of using geostationary orbits for satellite communication is attributed to none other than Arthur C. Clarke, the science fiction writer I quoted in our first lecture. Perhaps truth really is stranger than fiction. Now, it's important to recognize that there is only one geostationary orbit, 22,236 miles above the equator. And there are currently about 400 satellites in it. If these satellites were uniformly spaced around the circumference of the orbit, the distance between them would be more than adequate, over 400 miles. However, they're not uniformly spaced because a communication satellite needs to be more or less centered over its coverage area to do its job. Thus, GEO satellites are concentrated most densely over the most technologically developed regions of the world. In these regions, it's not unusual for GEO satellites to be separated by fewer than 5 miles. Given that they're moving at almost 7,000 miles per hour, this really isn't a lot of space. To minimize the possibility of collisions and electronic interference, each satellite is assigned an orbital station, which is really just a longitude, by the International Telecommunication Union. And as you might guess, a station in a geostationary orbit is one of the world's most prized pieces of real estate. But how does a satellite actually get inserted into its assigned orbital station? Well, to answer that question, let's follow the launch, deployment, and employment of a typical geostationary communication satellite. Along the way, I hope you'll come to appreciate the extraordinary sophistication in the design and production of these systems. Now, since the shutdown of the U.S. Space Shuttle program in 2011, all satellites are boosted into orbit by expendable launch vehicles. A variety of different commercially available rockets are used for this purpose. For our hypothetical mission, we'll use a typical example, an Atlas V rocket launched from Cape Canaveral, Florida. The Atlas V is a two-stage expendable launch vehicle built by the United Launch Alliance, a joint venture of Lockheed Martin and Boeing corporations. The Atlas V weighs over 700,000 pounds at launch, and it's capable of lifting a 64,000-pound payload into low Earth orbit or a 28,000-pound payload into geostationary orbit. Note that GEO satellites must be considerably lighter than LEO satellites because the geostationary orbit is so much higher. At the most fundamental level, a rocket engine is a simple application of Newton's third law. For every action, there's an equal and opposite reaction. Combustion of fuel causes high-pressure exhaust gases to be expelled at high speed from the engine's combustion chamber through a nozzle, which further accelerates the gases to supersonic speed. In the context of Newton's third law, the action is the rearward acceleration of the exhaust gas's mass, and the equal and opposite reaction is forward thrust, a force that causes the rocket to accelerate. A two-stage vehicle like the Atlas V is really two rockets, each with its own engine and fuel supply, stacked one on top of the other. When the first stage runs out of fuel, it's jettisoned, thus reducing the overall weight of the system and allowing the smaller second stage engine to accelerate the lighter vehicle to its final altitude and speed. Now, prior to launch, our satellite is folded up and stowed within a shroud at the top of the launch vehicle, as shown here. At launch, the Atlas V's first stage engine burns for about 4 minutes. The first stage is then jettisoned and it falls into the ocean. That's why it's called an expendable launch vehicle. The second stage takes over immediately, powering the payload into a circular, low Earth parking orbit, and then it shuts down. The shroud is jettisoned, and then the second stage engine is restarted to initiate an elliptical transfer orbit that will take the payload to geostationary altitude. To understand how this works, let's look at 3 relevant orbits. Let's say that the low Earth parking orbit has an altitude of 100 miles. We've already calculated the corresponding speed of this orbit at 17,500 miles per hour. In the desired geostationary orbit, the satellite will have an altitude of 22,236 miles and a speed of 6,877 miles per hour. To transfer from the parking orbit to the geostationary orbit, we need to design an elliptical orbit with its perigee at 100 miles and its apogee at 22,236 miles. Based on Kepler's laws, the speeds associated with this elliptical orbit can be calculated as 22,670 miles per hour at perigee and 3,600 miles per hour at apogee. Therefore, to transfer from LEO to GEO, we first execute a second stage engine burn that increases the rocket's speed from 17,500 to 22,670 miles per hour. This places the craft on the desired elliptical transfer orbit. The second stage would typically be jettisoned at this time. Now, because the satellite is now in an elliptical orbit, it slows down as it gets farther away from the Earth, reaching its minimum speed of 3,600 miles per hour at the apogee. At precisely this moment, the satellite must fire its primary rocket thruster to increase its speed to 6,877 miles per hour, at which point the vehicle assumes a circular orbit at geostationary altitude. So we've now got the speed and the altitude right, but this isn't a true geostationary orbit yet, because we launched from Cape Canaveral, located at 28.5 degrees north latitude. Our current orbit is inclined at 28.5 degrees to the equator. To achieve a true geostationary orbit, our transfer maneuver must also include a directional change that reorients the orbit into the plane of the equator. But merely achieving the geostationary orbit isn't good enough. We must achieve it at precisely the correct orbital station as assigned by the International Telecommunication Union. Doing so requires perfect timing of the engine burn that initiates the transfer. Now, commanded by a ground-based control center, the satellite now orients itself, deploys its antennas and solar arrays, senses the position of the Earth and Sun, establishes communication links, and becomes operational. The satellite is composed of two major components, the mission payload and the support platform, also called the bus. The bus is responsible for transporting the mission payload into orbit. It provides electrical power, attitude control, temperature control, and orbital adjustments. The satellite's attitude, that is, its orientation in space, is controlled with respect to a reference axis system that was actually borrowed from the world of aeronautics. The three axes of rotation are called pitch, yaw, and roll. The pitch axis is parallel to the Earth's axis. That is, a rotation about the pitch axis looks like this. The yaw axis is pointed from the satellite directly at the center of the Earth. So rotation about the yaw axis looks like this. And the roll axis is tangential to the orbit. So rotation about the roll axis looks like this. Now, the typical communication satellite has two large solar arrays, which serve as the sole source of electrical power in orbit. They're also used to charge batteries, which supply power when the satellite passes through the Earth's shadow. The arrays are oriented along the pitch axis, as you can see here, and they must rotate continuously on this axis, following the Sun as the satellite orbits the Earth. To see how this process works, let's assume that you are the Sun. And so with a satellite in this position, the arrays must be positioned like this so that they're oriented toward the Sun. Now, as the satellite orbits, the communications antennas must remain pointed at their designated coverage areas on the Earth's surface, called the footprint. And so, as the satellite orbits, the arrays must rotate continuously like this, even as the satellite continues to point toward the Earth. To control the satellite's position and attitude, the bus uses two separate systems, rocket thrusters and reaction wheels. This array of rockets typically includes one primary orbit maneuver thruster and 12 attitude and orbit control thrusters, arranged such that the bus can be propelled or rotated in any direction with great precision. These thrusters are used for the final insertion into geostationary orbit, for the initial orientation of the satellite, and for station keeping, the process of adjusting the orbit to keep the satellite at its prescribed altitude and longitude. Station keeping is required to correct naturally occurring perturbations in the orbit caused by the gravitational attractions of the Sun and Moon and by variations in the Earth's own gravitational field. Thrusters are generally not used for attitude control because they're powered by propellant, and when the propellant supply is used up, the satellite becomes useless. Today, there are many satellites in orbit that are fully functional but inoperable simply because they ran out of fuel. Rather than using thrusters, the bus controls the satellite's attitude with reaction wheels. Now let's imagine that this box is a satellite bus in orbit around the Earth. Of course, an actual satellite would be free to rotate about all of its three axes, pitch, roll, and yaw. But for simplicity, my model is only more or less free to rotate about its pitch axis, like this. And up above here is a reaction wheel, which is powered by an electric motor located inside the satellite bus. Now suppose we need to reorient the satellite about its pitch axis. I'll do this by increasing the motor's rotational speed. Sir Isaac Newton tells us that the resulting action, rotational acceleration of the wheel, will cause an equal and opposite reaction, rotational acceleration of the bus in the opposite direction. Watch. Notice how just a slight increase in the speed of the rotating wheel causes the bus to rotate as well. Now, my model has enough friction to stop that rotation of the bus eventually. But in the actual system, we'd have to decelerate the reaction wheel at the appropriate point to stop the bus's rotation at the desired attitude. So now, watch what happens when I decrease the speed of the reaction wheel. Notice that simply decelerating the reaction wheel now caused the satellite bus to accelerate in the opposite direction. And it's through this mechanism that the attitude of the satellite about its pitch axis can be very precisely controlled. My model has one reaction wheel, but a typical satellite has four, located as close to the satellite's center of mass as possible, and arranged with one each on the pitch, roll, and yaw axes, and one oriented on a diagonal to serve as a backup if any of the primary wheels should fail. Sensors continuously monitor the satellite's attitude, and controllers make minute adjustments to the wheel's speeds to keep all three axes oriented properly. Most important, because the reaction wheels are driven by electric motors, they use electricity generated by the solar arrays, and they don't deplete the satellite's precious supply of rocket propellant. The bus also includes a telemetry system that continuously transmits information about the satellite's status, attitude, power production, propellant supply, temperature, and so forth, to a command and control station on the ground. So, finally we come to the mission payload, the satellite's communications package. The basic function of a communication satellite is to receive radio signals, called uplinks, from a ground-based transmitter, amplify these signals, shift their frequency, and then retransmit them as downlinks to the Earth's surface. High-frequency radio waves propagate in straight lines. They can't bend around the curvature of the Earth. Thus, satellites facilitate the transmission of radio signals over long distances without having to use a string of terrestrial relay stations, as is the case with conventional microwave communications. The shift in frequency is needed to prevent interference between the uplink and the downlink. By the time the uplink reaches the satellite's altitude, its strength is quite weak. If it weren't for the frequency shift, the high-powered downlink would overwhelm the uplink. Communication services handled by satellites include TV, radio, internet, telephone, and some specialized business communications. Satellite telephone service is generally much more expensive than the use of landlines, cell phones, and undersea cables, particularly now with the advent of fiber optics. So, satellite phones are used primarily in remote areas that don't have other phone services available. Because the geostationary orbit is so high, there's a substantial delay in radio transmissions to and from the satellite, about 1/4 second each way, even though these transmissions travel at the speed of light. This delay can cause problems for two-way communications and certain types of data transmission, for example, internet gaming. But it poses no problems for one-way broadcasts like radio and TV, hence the growing popularity of these services. The mission payload consists of two main elements: antennas and a repeater. Most communication satellites are equipped with at least two dish antennas. These may be used for communications on two different frequency bands, or they may be aimed at two different footprints on the ground. But each antenna is generally used for both receiving and transmitting. Because radio signals are so weak by the time they reach the altitude of a geosynchronous orbit, these antennas must be as large as possible. Nonetheless, they're normally limited to a diameter of about 7 to 10 feet so they can fit inside the launch vehicle's protective shroud. As this diagram shows, the repeater includes a radio receiver, which receives the uplink and feeds it to an array of parallel transponders, each corresponding to a particular service: TV, voice, internet, radio, and a particular frequency band. Most repeaters have 24 or more transponders. Each contains an input filter, which separates out the particular signal that's assigned to that service, an amplifier, which boosts the strength of the uplink signal by as much as 10 million times, and an output filter, which performs the frequency shift required to prevent the uplink and the downlink from interfering with each other. By the way, these amplifiers invariably use old-fashioned vacuum tubes rather than transistors, because tubes are generally more effective in high-powered, high-frequency applications. This system communicates with a worldwide network of ground-based telecommunications ports, or teleports, which exist to provide customers with access to satellites. Equipped with antennas, transmitters, receivers, and routing equipment, the teleport receives signals from a variety of sources, like the public switch telephone network, the internet, and cable TV networks, and sends these signals as uplinks to the appropriate satellites. Similarly, the teleport receives satellite downlinks that originated elsewhere and routes them to the appropriate destination. But not all downlinks pass through the teleport. Over the past few decades, development of high-frequency, high-powered satellite transmission capability has stimulated the development of the Direct Broadcast Satellite Service, which produces broadcast signals capable of being received by the small dish antennas that have now become so popular with consumers. This capability, more than any other, is driving the continued economic viability of satellite communications. It's important to recognize that geostationary satellites aren't the only type of communication satellite. A relatively recent alternative is to use a constellation of LEO satellites, which are less expensive to launch, require less power for signal transmission, and are much less susceptible to the transmission delays associated with geosatellites. However, these systems require far more satellites to provide adequate coverage of the Earth's surface. A typical example, called the Iridium system, uses 66 of them. And because LEO satellites move at such high speeds, transmissions are constantly being handed off from one satellite to the next, in much the same way that cellular systems hand off calls from one cell to the next. In recent years, one of the greatest impacts of satellite technology on our everyday lives has been the advent of highly accurate satellite-based navigation through the Global Positioning System. The GPS was developed in the early 1970s by the U.S. Department of Defense for military use. But in 1983, President Ronald Reagan directed that the technology be made freely available for civilian use as well. Today, the system continues to be owned and operated by the U.S. government as a national resource, and the DoD is charged with operating and maintaining satellites, ground antennas, and control stations. GPS uses a constellation of 32 satellites in medium Earth orbit, flying at an altitude of 12,600 miles, with a corresponding orbital period of 12 hours. These satellites move in multiple orbital planes, such that any point on the ground theoretically has a line of sight to at least 6 satellites at any time, as long as there isn't a skyscraper or a mountain in the way. Each GPS satellite continuously transmits messages indicating the exact time of transmission and the exact position of the satellite at the time of transmission. The GPS receiver in your car detects this signal, and using its own internal clock, it calculates the time that was required for the signal to travel from the satellite to the receiver. Because electromagnetic waves propagate at the speed of light, this time measurement must be extremely precise. Yet no matter how precise it might be, this measurement can never be perfectly accurate because the clock in your GPS receiver can never be perfectly synchronized with the clock in the satellite. The inevitable difference between satellite time and receiver time is called clock bias. No doubt, you remember from your high school physics that distance equals rate times time. So once the transmission time is known, it can be multiplied by the speed of light, the rate at which radio waves are transmitted, to determine the associated distance from the satellite to the receiver. This distance is related mathematically to the positions of the satellite and receiver by this equation, which is really just the Pythagorean theorem extended into 3 dimensions. In this equation, x, y, and z represent the unknown position of the receiver in 3-dimensional space. X sub I, y sub I, and z sub I represent the known position of the satellite, and d is the distance between the satellite and the receiver. But d isn't really a known quantity because it includes the uncertainty associated with the unknown clock bias. So we need to rewrite this distance as the elapsed time plus the unknown clock bias multiplied by the speed of light. Called the navigation equation, this expression has four unknowns: x, y, z, and the clock bias, which I've called b in this equation. Thus, by the rules of algebra, this equation does not have a unique solution. But if the GPS receiver acquires independent position and time data from four satellites, we can write four such independent equations, and the resulting system of four equations in four unknowns can be solved. And this is precisely what your GPS device does. The receiver in your car is constantly listening for the position-time messages transmitted by that ever-changing swarm of satellites overhead. At regular intervals, it resolves the system of four navigation equations to determine your position in three-dimensional space. And then it displays this position superimposed over a digital map that's stored locally in the device. The device's other functions, determining a route, calculating the distance to your next turn, and speaking to you in that annoying voice, are also performed locally by the device's internal processor with no further interaction with the satellites. But of course, it's the satellites that make this amazing system possible. During this lecture, we've seen how our daily lives are influenced by highly sophisticated technological systems operating thousands of miles above the Earth. In the next lecture, we'll spend some time at the extreme opposite end of this technological spectrum, as we explore a potpourri of common household gadgets and gizmos, reflecting engineering applications that, if not quite as sophisticated as communication satellites, can be just as fascinating. For much of this course, we've been focusing on your home and on the large-scale infrastructure systems that support it. Today we're going to shift our focus quite dramatically from the technologies that constitute your home to the technologies contained within it, from large, complex engineered systems to small, simple products and devices. In making this shift, I hope to demonstrate that basic scientific and engineering principles are just as valuable to understanding mundane gadgets as they are for understanding large, complex systems. Now, by one estimate, each of us is surrounded by approximately 20,000 everyday things, from paper clips to pencil sharpeners to clock radios. And every one of these products has something interesting to tell us about everyday engineering. Now, we won't have time to cover all 20,000 in this lecture, so how might we choose a few representative examples from which we might learn something of particular interest? Well, as an organizing construct, let's build today's lecture around the classical simple machines, a concept that actually originated with the ancient Greeks and is still quite useful for classifying and understanding mechanical devices today. Although the official number of simple machines has varied somewhat through the ages, most modern lists include these six: the inclined plane, the screw, the wedge, the lever, the wheel and axle, and the pulley. All of these devices have the same fundamental purpose: to change the magnitude or direction of a force. Thus, to examine the simple machines rigorously, we'll turn to mechanics, the branch of science that deals with the effects of forces acting on physical bodies. In doing so, not only will we achieve a deeper appreciation for the many simple machines that are part of our everyday lives, but we'll also acquire some foundational principles of mechanics that will serve us quite well in later lectures. Let's begin with the inclined plane, or the ramp, which allows us to lift an object using less force than that object's own weight. Now, suppose we need to pull this wheeled cart up this 20-degree incline. The cart, plus the brick that's resting on top of it, weighs about 4 pounds. Now I'm going to use this spring scale to measure the amount of force required to actually pull the cart up the incline. As we can see, when I do that simple experiment, I'll pull on the spring scale, and you'll see that this 4-pound cart requires just a bit more than 1 pound to pull it up the incline. Looks like about 1.33 pounds. Why? In the science of mechanics, forces are represented as vectors. A vector is a mathematical quantity that has both magnitude and direction. For example, this force has a magnitude of 4 pounds, and it's directed at an angle of 20 degrees measured from the horizontal. For the purpose of analysis, it's often useful to resolve a vector into its perpendicular components, as shown here. These two components, horizontal and vertical, are exactly equivalent to the original force. We can calculate the magnitudes of these two components using trigonometry. For example, the vertical component is 4 times the sine of 20 degrees equals 1.4 pounds. But if you're